Okay, are you ready?
Yes.
Okay. So let us speak. Let us start AGEA seminar. Okay, the first speaker is Hwang from Institute for Basic Science. He will talk about the partial compactifications of meta-abelian Lie groups with the prescribed varieties of a minimal rational tangent. Then you start.
Okay, thank you. I like to thank the organizers of the East Algebraic Geometry East Asia for organizing this series of seminars and inviting me to talk today. Okay, so maybe the title is not very illuminating, so I explain basically the idea of, maybe I just to explain the title takes some time. So let me start with the motivation. What's the problem that I'm interested in? And for that, let me recall some basic definitions. And to simplify the matter, I will concentrate today mostly on the more geometric side. So I will work on more generally on complex manifold. X is a complex manifold. And of dimension n. And I'm interested in rational curves on X, and so especially just a simple case. So C is smooth rational curve. On X, and I say that this is unbendable. This is a terminology I define if this normal bundle of C inside X is isomorphic to O1 plus O for some non-negative integer P. So any smooth rational curve of normal bundle of this simple type, just O1 and O, is called unbendable. And why we are interested in such curves is there are many examples from algebraic geometry, and typically if you have a smooth projective variety, inside projective space, and then it's a complex manifold, and if it's covered by lines, meaning it's lines, some lines on the projective space cover X. Through every point of X, you can find line. Then a general line on X is unbendable. So this is the most typical example of unbendable rational curve. Lines covering smooth projective variety. So that's why we are interested in algebraic geometry, this type of rational curve. Now I will fix, to discuss the problem, I will fix K. This is an irreducible component. Of the space of unbendable rational curves on X. Just for convenience, I fix one component of unbendable rational curves on X. And this automatically means that they cover an open set of X, because unbendable rational curves can be freely deformed inside X. It can be freely deformed to cover some open set. So if I pick one component, then more or less they cover most of X. Okay, and then for general point, we can consider Kx, which is non-empty. This is members of K through X, through the given point. It's non-empty because just like what I said, unbendable rational curves can be deformed to open sets. So if you choose a general point, you have non-trivial members. And this is a smooth variety, smooth, actually, analytic set, smooth of dimension. The dimension is equal to sections of normal bundle vanishing at that point. So dimension of the sections of normal bundle vanishing at a point. So this is T, because there is exactly O1, T number of O1 factors. So this is a p-dimensional complex manifold. And then you have what's called tangent morphism. However, from Kx to the tangent space, projectivized tangent space, which is send an unbendable rational curve to its tangent vector. This is a map named tangent morphism, sending each curve to its tangent direction at the point X. And then this is an immersion. And then we define the image. This is an immersed submanifold. Immersed projective submanifold is called the VMRT of K and X. This is the abbreviation of variety of minimal tangent, but this is just a name. So we are looking at the tangent, the variety, the submanifold defined by tangent vectors to these unbendable rational curves passing through X. This is a BMIT, and this plays a very important role in understanding the geometry of rational curves. This is a very important object. So it's interesting to study what they are. So the main question I was interested in is this. So say question 1. Is what kind of here is the situation is rather general because we are looking at complex manifolds instead of algebraic variety. So what kind of locally closed complex submanifold in the submanifold in n-1 dimensional projective space, what kind of submanifold can arise as VMRT of some X and K. Okay. So whenever you are given a family of unbendable rational curves on a complex manifold, we have such projective submanifold. So the question is, what kind of submanifold are they? That is the question. And the answer is actually rather simple answer. Answer to question one is simple. That actually any submanifold of Pn minus 1 can be VMRT. So let's recall why this is so. So this is because you have the following construction. So if you are given S in Pn minus 1, now you consider Pn minus 1 as a hyperplane in Pn. And let X be the blow up of Pn along S. So this is a complex manifold. And then K is a proper transform of lines on Pn intersecting S and not lying on Pn minus. You consider such a proper transform, then this becomes a family of unbendable relational curves on S. And it turns out that Kx is isomorphic to Cx, and Cx in Px X. This is isomorphic to S in Pn minus 1. And in picture, what we are doing is here you have Pn, and here you have Pn minus 1, and you have S inside. Here's S. Now I blow up this S, so you have X. X has some exceptional divisor and some other parts corresponding to Pn minus 1, which is exceptional divisor. And then if you pick a point here, say a general point here, X, then the lines intersecting S leads to unbendable relational curve. And so exactly because of this reason, Kx is isomorphic to S. So all unbendable relational curves through X is exactly lines joining the corresponding point X to S. And so Cx in Px X is isomorphic to S in Pn minus 1. This construction actually works even if S is not algebraic. Just for any local submanifold, you can blow up. Then you can construct some submanifold, some complex manifold with a family of unbendable relational curves, such that its VMRT at the general point is exactly this given X. So the answer to first question is trivial. Any submanifold can be VMRT. So let's look at a slightly more interesting factor. The more interesting question is the following. Now, consider this situation. B is a subsheet of X, subsheet of complex X for some complex manifold. as before. So this is actually sometimes it's called distribution on X on complex manifold X, complex manifold. You are given a distribution on X. Now, instead of arbitrary unbendable rational curve, now we assume that members of K, so K is as before, is the family of unbendable rational curve. Now we assume that members of K are tangent to D, at general point. So these are, we are looking at unbendable rational curves whose tangent direction is actually inside the given specified direction. So let's see, this is rank D. Let's call this rank. Then what happens? Then the VMRT EX must be contained inside DX. By the assumption, it must be inside DX. So this condition means that CX is inside a smaller linear space. So now you can ask slightly different question. So question 2. What kind of submanifold? Now, this time inside D minus 1 can arise as VMIT over some X and K, but not arbitrary K, but K tangent to a distribution. We are asking slightly different question. Now, this is submanifold in P D minus 1, and we ask when this can arise as VMRT of unbendable rational curve tangent to some distribution of rank D. That is the second question.
A question? Question is so you assume you're trying to find an isotrivial VMRT or just at one point?
This is just a general point. The question is a general point. I'm not.
So it already implies isotrivial VMRT.
Well, you can say that. All right, you can. Yeah. It doesn't. For today's discussion, it doesn't make difference. You may consider isotrivial VMRT. All right. Thank you.
Okay. Thank you.
So that is the question, but the answer is also sort of as before. It's uninteresting because actually NES can do because the same construction as above. Wow. There's no difference. I mean, instead of S in Pn minus 1, you just look at P D minus 1. This is a special case of N minus 1. So you can just take inside the hyperplane and then take X to be blow up of S along blow up Pn along S. And then the same K as before. And you can see that this PD minus 1 on X, this PD minus 1 determines a distribution. Just to consider lines intersecting this PD minus 1, then they define a distribution such that K is tangent to B. The same construction as before gives answer to second question also. Given arbitrary submanifold in PD minus 1, you can make a complex manifold with a distribution such that all and then a family of unbendable rational curves, so all members are tangent to that distribution, and the VMIT is exactly S. Okay, so it's easy. Now the point is that this is somewhat uninteresting construction because this D, so this is the main point. This D is integrable. Integrable distribution, meaning that it is a foliation. It comes from complex submanifold. So basically, what you do here is the same construction, but we do it in a lower dimensional manifold. In that sense, it's uninteresting. So to really make the question interesting, you have to reformulate the question. So this is the really interesting question. It's almost the same as question 2. So what S in PD minus 1 can arise as VMIT for some X, K tangent to D, and distribution E in TF, which is not integrable. So that is the main point. We want to have an interesting question. You want the distribution to be non-integrable. If it's integrable, then the answer is easy. So what happens if we require non-integrable? So let me, well, some people are not so familiar with this non-integrable distribution. So let me recall the basic concept of non-integrable distribution. So this question is not so easy. This is the question we are interested in today. Let me recall the basic notion of non-integrable distribution. So we need the following definition. So D is a distribution. And then X is a general point. Then the Levy tensor of D at X is a homomorphism this is something we want to define. Levy tensor of D at X. This is something we want. This is a homomorphism which we denote by Levy D X. And this is a homomorphism from Levy square of dx, the tangent of D at X, to this quotient space. And it's defined by when you are given two vectors in Dx, this Levy tensor is, this is a homomorphism that stands UV to, this is how it is defined, to the Lie bracket of some vector field and take its value at x modulo Dx, where U tilde, V tilde are local sections of D. Satisfying its value at x is U, value at x is V, and this is Lie bracket over the vector field. Because U tilde, V tilde are sections of D. So these sub-sheaf of tangent sheaf, they are vector fields, local vector fields. So you can take Lie bracket and then take its value at the point x. And then this value at x depends only on U and V, not on the choice of this vector field. This value modulo Dx. This modulo Dx, it does not depend on the choice of this local section. It only depends on the vector U and V. So this is a well-defined homomorphism. And this homomorphism is called the Levy tensor of this distribution at the point at x. And then you have the classical Frobenius theorem, which says that D is integrable if and only the Levy tensor vanishes for all general points. So this Levy tensor measures the non-integrability of the distribution. So when we look for non-integrable distribution, we have to find a distribution with a non-trivial Levy tensor. Okay, so using this Levy tensor, we'll study this question. So what kind of submanifold can arise as BMRT tangent to non-integrable distribution? And there's a long time ago, there was a necessary condition for question 3 was discovered a long time ago. And this is a result I obtained with Naimimo in 1998, a long time ago. And it says the following: so if K is tangent to some distribution, then for general point in the complex manifold, the BMRT which is now a submanifold of this projectivized productization of V and X is isotropic with respect to this Levy tensor. So there's some condition it has to satisfy. It has to be isotropic with respect to Levy tensor. And this means what's the meaning of isotropic? Isotropic means that for any point in the affine cone of the VMRT and any two vectors in the affine tangent space of VMRT, so this is E here, this Levy form vanishes. This Levy tensor vanishes. So this VMRT as an affine variety is isotropic with respect to this antisymmetric tensor on Dx. Namely, any tangent to this, any two tangent vector to this VMRT must be annihilated by this Levy tensor. So this is a result we obtained a long time ago. So unlike question 1 or question 2, question 3 has some necessary condition. You cannot work with arbitrary submanifold. It has to satisfy some condition with respect to some antisymmetric form. Now, let me give one classical example, the most well-known example of such phenomena. And this comes from G theory. So G is a simple Lie algebra. And it's different from special linear algebra or simplex algebra. So type A or C is excluded. And then X is the adjoint variety of G. And this means it is the unique closed orbit in the projectivization of the Lie algebra G under the adjoint action. The adjoint action of the simple Lie group, the corresponding simple Lie group on the projectivized Lie algebra has a unique closed orbit that's called adjoint variety of the Lie algebra. And this X has non-trivial distribution over rank 1. And it's Levy form, Levy tensor. Well, this time, since it is rank 1, this is one-dimensional. So the Levy tensor determines an antisymmetric form on Dx, and this is a simplex form. There's natural simplex form up to constant space of scalar at each fiber of this distribution B, and this X is covered by lines, and they are all tangent to B. And the VMRT inside is cone inside this Dx is a Lagrangian cone. Lagrangian with respect to this symplectic structure, the symplectic cone. And exactly this Lagrangian means that it's isotropic So this is one example of this theorem where the VMRT, in that case, is lines covering the adjoint variety, must be isotropic with respect to this Levy tensor. And here it's indeed, it is the Levy tensor is symplectic form, and the VMRT, the affine cone of VMRT is a Lagrangian cone. So it is isotropic. This is a classical example of that theorem. And that theorem says that this picture is true in general for any unbendable relational curve tangent to a distribution. You have this isotropic property. Okay, so that is the situation. And so the question 3 has some non-trivial answer, that there's some non-trivial necessary condition to satisfy. Now the main result I like to discuss, report today, is exactly the converse of this. So this is the main theorem, and this is, so you may say that this is actually sufficient condition. And it's actually the same as this for question 3. So this, at least for the time being, it answers question 3 completely. This is the main theorem. This is proved last year, but it hopefully appears this year. Actually, this morning I put it on the archive. The paper is on the archive. And it can be formulated as follows. We consider a d-dimensional vector space and n minus d-dimensional vector space, two vector spaces. And we consider any homomorphism from W, where the scale of W, 2. This is any homomorphism. And I consider a submanifold inside PW, which is isotropic with respect to omega. What does it mean? Well, the same meaning. So for all points in the affine cone and any vector in the tangent to the affine cone at that point, which is which are vectors in W, we require that they are annihilated by omega. This is the requirement. This isotropic is equal to omega. That is the condition that appeared in the necessary condition. Now here we have this, the same condition here. Suppose you are such a situation. You are given any antisymmetric vector valued antisymmetric form, and you are given some submanifold, which is isotropic with respect to this omega. Then there exists a complex manifold X. And distribution or rank D. And K is as before, this is the irreducible component of unbendable relational curve on X. Such that for general point, and this K is tangent to D. Except for general point, the VMRT is isomorphic to X. exactly the given S can be realized as VMRT tangentially, and the Levy form is isomorphic to omega. The Levy form is exactly isomorphic to this given antisymmetric form. So this is sort of gives the converse of this theorem. The converse of this theorem. So whenever you have isotropic submanifold with respect to some vector valued antisymmetric form, you can realize it as a VMRT of some unbendable relational curve tangent to some distribution of the same rank as W, such that the VMRT is the same and the Levy form is the same. Okay, so this is the main theorem, and now you can. Okay, so this is the main theorem. So let me discuss now the idea of the proof of this. So the proof is probably more interesting. Any questions so far?
So in this construction, so X is not necessarily projective.
Yes, thank you. I will discuss it actually at the end of the, I plan to discuss it. At the moment, this X is not projective variety. It's just complex manifold. Thank you.
Okay, another question is, so you may have two such X, so can you relate them?
You may not necessarily. I did not consider such a question at the moment because you see, I don't think the answer is positive. What you said, but I don't have examples. But probably one can. There are examples with this property. I mean the same VMRT, but all right, okay. I cannot give you very interesting example now, but I doubt. I don't think it's unique. This is just one construction. I don't think it's unique. Any other question? Okay. Now let's discuss what's the idea. How to find such a and such B. Okay. Now the idea is, you see, the result with the 9 more was like more than 20 years ago, and actually, right after we obtained the result, we are interested in this kind of question. And why it took so long? So the question is how to generalize this? How to generalize this construction of blow up of Pn along a submanifold S. How to generalize this to non-integrable distribution? That was the question, and I looked at this for a long time, but was not successful. One reason is that we are too much sort of confined by the idea of blow up. So I thought that it must be some kind of blow up, starting from this given S, subspace, and that is it didn't work. So all kind, maybe instead of ordinary blow up, maybe some some directional blow or something like this. But it didn't work, and only recently I get the correct viewpoint. Then it's easy. So the correct viewpoint is actually simple. This blow up of Pn. This is equivariant compactification of a vector group. Yeah, abelian vector group, which is just a complement of this type of plane. So what really happens here is kind of a compactification of Cn, is complement of Cn minus 1, complement of this Cn minus 1. This gives a way to compactify this vector group in such a way that only a given direction becomes unbendable relational curve. Now, usually Pn itself, Pn is a compactification of Pn. This is also equivariant compactification of Cn, such that all lines becomes lines. Okay, that is the original idea of compactification. Pn, the projectivization is that you want to make all affine lines on Cn into a projective line. That is the idea. But the blue of S is exactly you want to select some special direction and make a compactification such that only lines in this special direction or becomes line. So that is the viewpoint. So the idea behind this result, new result, is just very simple. Is what we want to do is we want to this X in main theory is a partial compactification equivariant compactification of a non-abelian group. So you choose a suitable group and then suitable non-abelian group, and then you compactify it in such a way that a given direction is specified, arise as a line. So the idea is this. So given this omega, we are given this vector values antisymmetric form. Define Lie algebra. Lie algebra is just W plus Q direct sum, but with the Lie bracket. The Lie bracket is defined as follows: W1 plus Q1, W2 plus Q2. If you take this Lie bracket, the Lie bracket is just omega W1, W2. That is the Lie algebra. So this is called such Lie algebra is called metabelian Lie algebra. So by Lie theory people, they call this metabelian Lie algebra. It's the simplest non-abelian Lie algebra. So this is sometimes it's called the two-step graded nilpotent Lie algebra. Just there's two grading. It's the graded Lie algebra with two steps. And then we call G simply connected group of this Lie algebra G. So this is called metabelian Lie group. And the group multiplication, G is also just as a complex manifold. It is just a direct sum of W and Q. And the group multiplication is This is just W1 plus W2 plus U1 plus Q2 plus half of omega W1. That's the group multiplication. It's non-abelian group. Okay, now, and we want to compactify, equivariantly compactify such non-abelian group. Not completely compact, but some partial compactification of this non-abelian group. In such a way, the only lines in a specific direction becomes unbendable relational curve. Now we are given this affine cone of this given submanifold S in W, and if you are given a vector here and X in G, we have L, Y, X. This is affine line with G in Y direction and through X. This is the definition of this is just it is X at exponential of C Y. If you are given, now this is inside D algebra G W. So given vector Y, you have its exponential one parameter subgroup, and we multiply it by X. So what you do is here you have G, and this Y is just a tangent vector here, and then you have this exponential. This is exponential subgroup. So it looks, this is actually, if you compute, it becomes an affine line in G as an affine space. And then we shift it to X, some X here. X. This is X. This is a line in the Y direction through X. So this way you obtain many lines. And such lines are called, so these are called S line on G. So it's very similar to the concept of affine lines in the equivariant compactification of vector group. If here we consider certain lines in the given direction, you consider all family of such S lines on G. Then this W, you have this S inside W inside G, and this gives rise to left invariant subbundles. So say S W inside G. So this is a left invariant distribution on G. And if you compactify, you have some submanifolds in W inside G. And these are exactly directions tangent to S line. This submanifold, this looks like VMRT now, but only is happening on some affine variety. We are collecting all such lines and their tangent vectors. It becomes this left invariant subbundle inside the productivization of this distribution. So we have now, and these are also you can regard it, say, let's call this R. Then we have this is the universal family of S lines on G. So this is affine variety, and we have affine lines on affine variety G. And we consider the universal family of all such affine lines, S lines. And they form an algebraic variety. And so you have such an algebraic map. So the fibers are, so this mu is just projection from this projectivization. And this law gives the parametrization by all face of S lines. So this law is a C bundle, I mean A1 bundle. Each fiber is affine line. So that is the situation we are in now. And then the idea is now partially compactifying. Okay. First, you compactify this S to R. This is A1 bundle. But we can compactify it to P1 bundle on R. And then extend mu to mu bar to some compactification of G. And the compactification actually of G is constructed by using this P1 bundle. This P1 bundle contains a special divisor at infinity. And we use this this map, this partially compactified P1 bundle to construct this G bar. It is somewhat complicated to discuss the details, but that is the idea. Now, what you may wonder why this condition, isotropy, is needed. Because so far, all the construction seems to work for arbitrarily given submanifold. Arbitrarily given submanifold S, you can consider such a family of affine lines. You have such universal family, and you can make this A1 bundle into P1 bundle. It seems to work very well. The problem is at the very end, if you start with arbitrary submanifold S, it does not give unbendable relational curve. This quotient, this map becomes rather complicated and makes trouble. So the key point of this isotropic condition the key issue, role of omega isotropy. S must be omega isotropic. So why is this important? The main issue is that when you geometrically, when you look at this S, this G, and this you have this from X. Now this is say S, X, and X, and you move it to exponential, say Ty. Yeah, so this Lyx. This is S, X. Okay. So you compare this S at two different points along the line, then you have a corresponding lift. This is lift, tangential lift of this line here. This is the picture, and the key point is that if you start with a vector here, tangent V, to understand what these curves become when you project it to a compactification of G, depends on how this V moves as you move along this line by the right exponential action. this V becomes some V prime. So by right action of exponential ty controls the geometry of this image of the closure of this affine line in G bar. When you compactify this, what kind of rational curve it becomes, it really depends on how these vectors move along this line as you translate it. And since this is non-commutative group, the nature of this right action in compared with this left invariant submanifold, and this becomes unbendable, only when this omega y and z vanity. Only when this becomes as is omega isotropic, it's move along, this behaves nicely, so that its closure becomes unbendable. That's why we need this isotropic condition to obtain unbendable. Okay, thank you.
Okay, thank you for the. Let us thank to the speaker. Is there any question or comments?
Yeah, I have a question. So if you take this pure meme, this example you mentioned, so with your construction, what do you obtain? If you take this adjoint variety.
Okay, it actually, in the adjoint case, the group is Heisenberg group. And you are given a Lagrangian cone for the Heisenberg group. And if you carry out this construction, it must agree. This construction must give an open set inside the adjoint variety, outside some codimension 2 set.
Okay, okay.
So it recovers adjoint variety. If this S is chosen as a VMIT of adjoint variety.
Okay,
if you
okay.
carry out that construction, you obtain an open set inside the adjoint variety, outside some codimension 2 set.
Okay, okay, thank you. So another question is, in general, so what do you obtain X? What's the bigger number of this X now?
I'm sorry, but this X is complex manifold, unfortunately. And it's not compact at the moment. But what I can prove is that if S is a projective submanifold, you see, the construction of X depends on S, choice of S. And our choice of S is arbitrary analytic complex submanifold. So
okay.
This X is very far from algebraic. It's just, it can be very transcendental. But if you start with smooth projective variety S, and you carry out this construction, then you obtain a complex manifold which is metamorphic to a projective variety. So a Moise-Jordan space, you obtain Moise-Jordan space. But I cannot prove, I don't know the Picard number. The Picard number is usually big, can be big. And I don't know whether when it really becomes projective algebraic or not, I don't know. So all I can show is that you obtain some complex manifold, which is Moise-Jordan. It's bidirectional to algebraic variety.
Oh, okay, okay, thank you. Thank you.
Okay, are there any questions?
Excuse me?
Yes.
For higher nilpotent, your compactification is inductive one. Could we do it step by step?
That's a good question. That's a good question. So my construction is only for 2-step nilpotent group. I haven't tried the higher nilpotent when there are more steps. I haven't tried it. I think it should work, but I haven't tried it because if you look at my construction, my paper is done by very explicit computation. So I do not want to general statement. I just want to one construction and as simple as possible. So I didn't look at higher steps. I think it should work for nilpotent graded nilpotent algebra over higher steps. It should work, but I don't know. I cannot say. I haven't proved that case. So it's an open question. What you asked is at the moment is an open question. Okay.
Okay. If no question, then let us thank to speaker again.
Thank you.
Thank you for the speaking talk in this seminar, Hwang. 고맙습니다. Okay.
Yeah, yeah.
We
Thank you. Thank you for listening.
okay. The second talk